quantum noise.
Thank you. Yes, I changed the title a little bit and also the topic slightly. I hope you will forgive me for that.
Speak up, please.
Okay, I will try. So I'm going to report on work with several students of mine, Sirvash Ashlambegi and Mehdi Saravani of the University of Waterloo, where I am based, Tej Al-Bhamra of Princeton, David Asen, who's now at Caltech, Adrian Chatwin Davis, who's at Caltech, and Robert Martin, who is at the University of Cape Town. The most recent paper that I will talk about today was just accepted yesterday in PRL. Let me start with a bang. The talk will be about this, more or less. So you all know what happens next. A huge sound will come out of this. And one of the questions that one may ask is, if you didn't see the scene, but you heard the sound, what could you tell about the bell? You could probably quickly tell how big it is, or how small it is. But before the advent of quantum mechanics and before general relativity, Hermann Weyl already asked the question, how much can the sound tell about the shape? And that founded the field of spectral geometry. How to get the geometry of something from its shape. From its sound, from the sound it makes when tapped. Now let us, this was in 1904, 1905, I think, that Hermann Weyl started that field. Now let us upgrade that question and modernize it. How much can quantum noise, the quantum fluctuations of a quantum field, it's a kind of noise, a kind of sound, how much can it tell us about the curvature of a space-time on which it lives? You see, when space-time is curved, this will affect the quantum noise of fields that live on it. So the question I'd like to ask is, how much does this quantum noise know about the curvature of space-time? Now, how could this possibly work out? Let us start with quantum field theory on flat space-time to keep things simple. I mean, the experts among you in that field will find this slide boring, but for others it might be interesting. So let us consider the Klein-Gordon equation there. Just the Klein-Gordon equation. And let's assume space-time for simplicity, not for essential reasons, but just for simplicity, to be discretized for the moment. Then, also for the moment, drop that term. Let us assume it's not there, this term with the Laplacian. Then what does the Klein-Gordon equation become? Well, for every point in space, it now becomes the equation of a harmonic oscillator. So what we have is that at every point in space-time we have a harmonic oscillator. However, we do have this term in reality, and that term will couple those neighboring oscillators to another. If you think of space-time as being discretized, this Laplacian becomes a finite difference operator, and therefore we have coupled harmonic oscillators. Now, the ground state of a system of coupled harmonic oscillators is, of course, an entangled state. Therefore, a quantum field is entangled even in its vacuum state. The quantum fluctuations at this location therefore be correlated with the quantum fluctuations at a nearby location. They will even be correlated to some extent to quantum fluctuations far away. There is short-range entanglement. It actually ranges arbitrarily far, but it decays pretty quickly. We can measure this entanglement in many ways, but one way that it expresses itself is, for example, in the two-point function, which simply quantifies the correlations between the fluctuations of different points. A few remarks, what that can be used for. Well, the fact that this entanglement is short range leads directly to the area laws, the famous area laws that for entanglement in the vacuum. And that's because if you slice through a region of space-time, then you pick up entanglement entropy from where you slice, but not so much from outside, and that leads to the area law. The area of the cut. And that, of course, has connections to holography. On the other hand, what this also means is that you can harvest entanglement from the vacuum. You can even farm entanglement. You can repeatedly harvest entanglement from the vacuum. And you can use this for all sorts of purposes, such as quantum computing, in principle. But also, you can use this to do a procedure that is called quantum collect calling, where you can send information without sending energy. In fact, the recipient has to spend energy to receive the information. And then there's the phenomenon of quantum energy teleportation, also based on this structure, which holds that you can make a measurement here, send information about it over there, then somebody can use that information to draw in energy out of the vacuum, basically because the system has become rigged now. You can predict the next quantum fluctuation because it was entangled with where you did your measurement. Now, I have papers on all these subjects, but I don't want to talk about this today. It's fascinating stuff. All of these are, of course, fields on their own. The question was a different one, namely, how to get to the shape from the sound, or how to get to space-time curvature from the quantum noise of the fields that live on it. So how could this work? Now here we have the Klein-Gordon equation on a curved space-time, and what you see is that, of course, this makes the argument of before much more non-trivial. Now we have significant coupling between those harmonic oscillators. No, sorry, we always had coupling, but the coupling is distorted now. The coupling between neighboring harmonic oscillators, field oscillators, is distorted, and that means that the entire mode structure is correspondingly distorted. The quantum fluctuations feel that. So the curvature affects the correlations of the quantum noise. And this also means, for example, that the curvature of space-time affects the propagator of whatever field you're considering, for example, of a Klein-Gordon field. So then let's ask, how much does the propagator know about the curvature? Imagine that we know we have a curved space-time, but we do not know the metric. However, in some coordinate system, we are given a two-point function. Let's say we are given the Feynman propagator, but we don't have the metric. Then from the Feynman propagator, what can we do? It turns out you can get the metric back. And here is the formula for how you can do that. This is the Feynman propagator here. You take it to a certain power, 2 to the power of 2 over 2 minus capital D, where D is the space-time dimension. This formula is true for D larger equal 2. There's also a formula for D equal 2, but then there's a logarithm involved. In effect, the Feynman propagator for a scalar field can play the role of the Singe world function. This works because the propagator measures indirectly the distance between two events. The further they are apart, the less the quantum noise is correlated. The closer they are, the more it is correlated. And if you do know the distance, you know the metric. And if you know the propagator, you have a measure, a monotonic measure of the distance. That's why this can work. So you can express the metric in terms of derivatives of the Feynman propagator. This is a scalar function. Now, normally when you take second spatial derivatives, the second derivative has to be a covariant derivative with the Kurzhoffer symbols. But not in this case, because this is a biscalar, and we differentiate only once with respect to each of the variables, and then we take the coincidence limit. It's not really a very complicated result. You can derive that pretty easily. Just use geodesic coordinates, use covariance, asymptotic behavior of propagators, and so on. In the paper, we also have worked out examples of this. So what this means is that, in principle, you could replace the metric by this expression in terms of the Feynman propagator whenever you want. But remember that there's nothing quantum about the space-time at this stage. It's just recovering a classical background space-time from the correlations of a quantum field that lives on it. A remark. I think this has a kind of philosophical beauty to it. Let's consider that Einstein built relativity very carefully, matching the mathematics that he developed to actual physical experiments that boil down to having normalized rods and clocks that are synchronized in particular ways. And ultimately, he always made sure that there's a map between rods and clocks on one hand and the mathematics on the other hand. But of course, at subatomic scales, there are no rods and clocks that we could use, even in principle. Nevertheless, we like to imagine them to be there, but there aren't any. And what this little calculation that I just showed demonstrates is that you can replace clocks and rods. Instead of measuring the space-time using clocks and rods, what you can do is you can use the quantum fluctuations of a field. And then by keeping track of how correlated they are, you get the distances. And if you have the distances, you have the metric. Another remark is this, which leads us into yet another direction, but I think it's an interesting remark. Let us get back to the question that Hermann Weyl asked more than 100 years ago. Can you tell the shape of a bell from its sound? And in this case, it would be, can we get the curvature of space-time, can we get the metric of space-time, not from the propagator, but instead just from the spectrum of the quantum noise. The propagator has much more information than the spectrum. Could that be sufficient? Well, it turns out that in certain circumstances, yes. If the signature is Euclidean, then we can do it. However, the spectrum of the quantum noise of a scalar field will not be sufficient. What you need in this case is the spectrum of both scalar fields, the spectrum of the quantum noise of vector fields, and of covariant symmetric two-tensor fields. If you have those, then you can reconstruct the space-time metric in infinitesimal steps. This is a larger field, and there are several papers on this, but let me just give you the gist of it. This field is an old field. Spectral geometry is more than 100 years old, and a lot of results are known in there. However, it used to be stuck in some sense, in that some positive results were known about manifolds of low dimension and just negative curvature, for example. On the other hand, counterexamples were also known in high dimensions. But mathematicians have this habit of either proving or disproving things. And spectral geometry is so hard that it is difficult to prove and to disprove things. It is so hard because it's so tremendously nonlinear. If you're given a differentiable manifold, it's already a difficult problem to calculate the spectrum of a Laplacian on it. But try to do the opposite. Try to get to the differentiable manifold from the spectrum. Doesn't even know, I mean, one usually doesn't even know how to start. If you give yourself enough symmetries, you can do things. But then you're stuck with very special cases. So what we did in order to get spectral geometry unstuck and to get a better feel for what the generic situation is that we introduced something into the field that mathematicians usually don't like, which is perturbation theory. So we said, instead of trying to solve the full nonlinear problem all at once, we said, let's try to solve a more modest problem. Instead of saying, give me the spectrum, I calculate the shape for you, which is too hard, we said, assume we know the shape and we know the spectrum, both of them. And then somebody changes the shape a little bit and tells us how the sound changed a little bit. Then our task is to calculate the change of shape from the change of sound. This now is a linear problem. If you just do an infinitesimal change of shape, it comes with infinitesimal change of sound. And if you introduce an infrared and ultraviolet cutoff, it's actually a finite dimensional problem. You end up having to invert a matrix and checking when it is invertible, and that can be done. And that's how we found out which types of spectra you need in order to be able to invert it, and what was missing there, and why it works in 2 dimensions and not work in higher dimensions, and so on. Anyway, that would be spectral geometry, but I wanted to go in a slightly different direction. Spectral geometry, though, I think is a very promising mathematical tool for physics, and the reason is that ultimately, if we are to unify quantum theory with general relativity, then that unifying theory must also unify the mathematical languages of the two. And the mathematical language of general relativity is, of course, differential geometry, and that of quantum theory is functional analysis. They are as different as the physical theories are. But spectral geometry very naturally combines them. It's about the differential geometry of a manifold and the functional analysis of operators that live on it. Anyway, let us move on. Enter Planck scale physics. What happens to what I just discussed if we add the assumption that there's an ultraviolet cutoff in nature, that there's a natural ultraviolet cutoff? And I'm not going to make any assumptions. I'm not going to risk guessing the right theory of quantum gravity, be that loop quantum gravity or string theory or whatever other approach. Instead, I'm going to try to build on just general relativity in quantum field theory and curved spacetime and work from the infrared, basically from the safe territory where we know how things are. And then I'll ask, how could Planck scale physics first manifest itself as we increase the energies and approach the Planck scale? So what kind of natural ultraviolet cutoff could we encounter as we push quantum field theory towards its limits? And I'm going to make an assumption here, which is usually not necessarily made, but I want to insist on it here, which is that we keep local Lorentz invariance. It's easy to break, it's easy to put cutoffs in there, but if you break local Lorentz invariance, it's hard to tell whether the effects that you get are because of the ultraviolet cutoff, or maybe they are simply because you're breaking local Lorentz invariance. So I'm going to insist on local Lorentz invariance, and that means we have little choice in how we put the ultraviolet cutoff into the quantum field theory. It basically boils down to doing something with the spectrum of the D'Alembertian for a scalar field, if we are working with a scalar field. So we can basically suppress the high momentum squared, the close to Planck scale eigenvalues of the D'Alembertian, or we can cut them off. Let us look at the most extreme case to get the most pronounced signature. Let us assume that we cut off the spectrum of the D'Alembertian. Now you might think, okay, if you do a momentum cutoff, or energy momentum cutoff, you might expect a lattice. But that's not so. If you do implement a momentum cutoff, you only get a lattice under one condition. You have to impose periodic boundary conditions in momentum space. But that's a little weird. Why would we have periodic boundary conditions in momentum space? Let us consider instead Dirichlet boundary conditions in momentum space. In that case, the benefits we get is that this describes a covariant generalization of something that's been discussed very much in the literature, which is minimum length uncertainty principles, as they arise from quantum gravity arguments, as they arise from string theory. Also, if we require Dirichlet boundary conditions, we obtain a covariant version of what in engineering is called Shannon sampling theory. Shannon sampling theory is the mathematical bridge between discrete representations of information and continuous representations of information. It's perhaps the most used theorem ever because every computer is using it for all analog digital conversion. And the theory behind that is a cutoff with cutoff in momentum space or cutoff in frequency space with Dirichlet boundary conditions. In that sense, then, just like a musical signal can be sampled, if it's band limited, it can be sampled at discrete points in time and yet reconstructed without any error as a continuous signal. In the same way, space-time with this kind of cutoff becomes discrete and continuous simultaneously, in exactly the same way that information can be simultaneously discrete and continuous, just like music. So, let us do this. Let us introduce a cutoff on the D'Alembertian. And concretely, we can do it this way. In the path integral formulation, let's just consider a scalar field for now. We have here the action, here we have a source term, and now we do the usual path integral, except we are not path integrating over all field configurations, but only over a certain subspace of that function space. And that subspace we choose to be the function space spanned by the eigenfunctions of the D'Alembertian, whose eigenvalues are bounded, whose eigenvalues are within an interval characterized by some lambda, by some ultraviolet cutoff, by some finite natural ultraviolet cutoff. You can view this as saying that in the path integral, we are normally not only summing over the classical field configurations, which extremize the action, even though they contribute most. In the path integral, we are also summing over all field configurations normally. Now, with this cutoff, we are not summing over all field configurations. Those that are too far off shell are now removed. We could also suppress them, but let's do the extreme thing and just remove them. So the first thing we did then is we applied that cutoff to the calculation of the metric from the Feynman propagator. And you see, one thing you notice here is that in the calculation of the metric, to recover the metric from the Feynman propagator, we had to take this coincidence limit. Take the derivatives with respect to both arguments, then the coincidence limit and some decorative factors here. That coincidence limit is an ultraviolet limit, and that competes with the implementation of the ultraviolet cutoff. And it turns out they don't commute the two limits. And of course, we shouldn't take that coincidence limit. If we perform this natural ultraviolet cutoff, we are basically saying that we have a cutoff. We are not able to perform coincidence limits, so we shouldn't take that limit. And if you plot what you get, you find this in the particular example where you can do things analytically in D equals 3 flat Euclidean space. The metric that's reconstructed without taking the limit, or before taking the limit, when the distance between x and y is here on the x-axis. And you see that the metric has two contributions, the one that's expected plus another contribution here. And we obtain that these prefactors, f1 and f2, are oscillatory. All what this means is that we recover the metric even with the ultraviolet cutoff, but only if we average. If we smear, if we take into account that we can't really resolve to arbitrary accuracy. The oscillations themselves can easily be understood. Basically, if you don't take the coincidence limit, but you're this far apart, x and y, then you can ask, how often does the Planck length fit in there? And then I make it closer. How often does it fit? You see, sometimes it fits in integer times, sometimes fits in half integer times, then in integer times, and so on. And this will be the oscillations then. Anyway, this is obviously not going to be measurable at the LHC. The Planck scale is more than a dozen orders of magnitude, thank you, more than a dozen orders of magnitude away from measurability at the LHC. So where might one possibly measure such an impact that a natural ultraviolet cutoff might have on space-time, on fields, on the propagator? Sorry, I didn't give credit for the image, but it's as iconic now as is a picture of Einstein, so it might be. Okay, so the idea is this, and of course, that idea has been discussed a lot. This structure ultimately, if inflation is right, originated when co-moving modes were crossing the horizon. And that horizon, the Hubble length, during inflation might have been only about 5 orders of magnitude away from the Planck scale. And therefore, there is a chance that there is a 10 to the minus 5 impact on the CMB from Planck scale physics. So let's ask, if we implement this very simple, straightforward, just covariant cutoff, what would it do to the CMB? And would it be first order? You see, the critical scales involved are the Planck scale and the Hubble scale during inflation. And their ratio is dimensionless. So then the question is the effect going to be first order or second order in this? If we are lucky, it's first order, and the effect might be 10 to the minus 5, and conceivably sometime measurable. But if it's second order, it would be like 10 to the minus 10, and I don't think that would ever be measurable. So over the past 10, 15 years or so, people have looked at this question and they have implemented various candidates for natural ultraviolet cutoffs in inflation and have come up with predictions for how the spectrum might be changed for both the temperature and the B modes. Unfortunately, no agreement has been reached on this question, which is perhaps also not surprising because different ultraviolet cutoffs have been tried. But also no agreement has been reached on whether the effect is first order or second order in the ratio of Planck over Hubble length. So it could be an effect of the order of 10 to the minus 5 or 10 to the minus 10. So the challenge has been to calculate these predictions without breaking local Lorentz invariance. After all, if we do break local Lorentz invariance, the effect we see might be just because of the breaking and not because of the ultraviolet cutoff. So we wanted a clean situation and kept local Lorentz invariance in the way that I just indicated with cutting off the field configurations in the path integral. And our paper was just yesterday accepted. That's why I changed the talk a little bit, just to celebrate that paper a little bit. And that paper was with Aidan Chatwin Davis and Rob Martin of Caltech and University of Cape Town. What we found is that, again, there are oscillations. So if we have power law inflation, for example, that's the only doable case, then the relative change in the tensor spectrum, but it would be very similar for scalars, would be given by a curve like that. Now, never mind the details. The key point here is, thank you, the key point I want to convey is that it's first order. So what we found is that these oscillations that will be imprinted on the inflationary predictions for the spectrum are going to be first order in amplitude, first order in the ratio of Planck over Hubble length, and therefore maybe 10 to the minus 5, maybe in the far future we might be able to measure such a thing. So last slide, the conclusions. First we asked, does the quantum noise of a field living on space-time know all about the space-time curvature? Yes, it does. It knows all about it. It just, even from the scalar field free propagator, you can recover the metric. And in the Euclidean signature case, a certain collection of spectra alone would also do it. But also, we found that the propagator tells us more. The propagator tells us not just, it doesn't just allow us to recover the metric, but also if we put an ultraviolet cutoff and then implement that in inflation, then the propagator which is used, the two-point function is used to calculate the actual CMB spectrum or the seeds for the CMB spectrum. So the propagator also has the ability, conceivably, to indicate to us experimentally the onset of Planck scale physics. 10 to the minus 5 away from it. Thank you very much.